Hi, and welcome back to my channel. This week's problem is about trying to find the blue area. Now, that blue area is made up of a large semicircle of radius 2, and we have got three yellow semicircles on top of that, overlapping each other with radius of 1, and they're congruent. They are identical semicircles. Now, the left and the right-hand side of the middle yellow semicircle touches exactly the centers of the left and right semicircles, the yellow ones. Now, the reason I've chosen this problem is because I've seen a problem in the same style on GCSE papers before. Not exactly the same as this question, but using the same principles. And so I thought it would be good, particularly with the students at the school I work at the moment, coming up to mock exams, to go through a problem like this and show you how to approach it, how to solve it. Now, if you want to have a go yourself, pause the video now. Otherwise, I'm going to go through my solution, show you my solution in 3, 2, 1. Okay. So the first thing that I would do with this problem is I would draw on the radii. Now, we've got the radii going from the center of this left-hand semicircle. We have got the radii going from the center of the right-hand semicircle. And we have got two radii going from the center of the central yellow semicircle. So these lines here. Now, by symmetry, I have got also two triangles here. So that is using the symmetry of the left and the right-hand semicircles, okay? Because obviously the semicircles have got a line of symmetry down the middle. So I can likewise have these two triangles. Now, from there, I can also join the apex or the top of these triangles. Now that's going to make three upside down triangles as well, which should become more clear in a second where they are, but essentially they're here, here, and here. Okay. Now I want to start labeling this and marking on what my radii are. So these are my radii. They have got a length of 1 because that is the same as the radii or the radius of the yellow semicircles. Now, by symmetry, I've also got that these have a length of 1. And from there, well, if I've got all three sides of the same length, then I must have an equilateral triangle. And so these angles must be 60. And again, by symmetry, these angles must be 60. Now, from there, if I look at these points here, so that angle, this angle, and this angle, well, I can work those out by doing 180 take away 260s, and that will give me 60 degrees. Now, if I just look at one of these upside down triangles here, they're all going to be the same. So if I just look at one of them, well, I've got 60 degrees here, and I've got two sides which are the same length. So I must have an isosceles triangle. So I do 180 take away the 60 and split it in two. 180 take 60 is 120, divided by 2 is 60. So I get these angles as being 60. Well, that means I've got three angles that are 60, and so it must be an equilateral triangle now, not an isosceles triangle like we thought. So the top side of those upside down triangles must also be the same, must also be 1. Now, I'm going to make this a little bit easier to see here. But what we can see is we've got lots of the same triangle, and we've got some other things called segments, which are the curved bits outside of that triangle. Okay, so the area of one of these small triangles is going to be half AB sine C, which is the trig way of working out the area of a triangle. So a half times one of the sides times another side times sine of the angle in between. So half times 1 times sine 60. And that is root 3 over 4. Now let's put that to one side for the second, because we need to work out the area of one of these segments. And we can do that by doing the area of a sector minus the area of the triangle. Now, a sector is going to be like this. Okay, so it includes the curved bit, if you're not sure. So, first of all, we need to work out the area of the sector because we've got the area of the triangle. So, area of the sector is angle over 360 times pi r squared. So 60 over 360 times pi times 1 squared. And that gives us pi over 6. And again, let's put that to one side. And we said before the area of the segment is the area of the sector minus the area of the triangle. And we've got both of those things. So let's substitute those values in. And we get pi over 6 minus root 3 over 4. Again, let's put that to one side and keep that safe for the moment until we're ready to use it. Now, we have got the area of the triangle, we've got the area of the segment. Now, all we need to work out is the area of the blue semicircle, and that is going to be 1/2 pi r squared. And the radius of the blue semicircle is 2, so it's 1/2 times pi times 2 squared, which gives us an answer of 2 pi. Now let's tidy everything up, collect everything to the right-hand side. All we need to do now is take away the area of the triangles, the area of the segments from the area of the blue circle. And, well, how many triangles we got? 1, 2, 3, 4, 5, 6, 7 triangles, and we have got 1, 2, 3, 4, 5 of the segments. So we're going to do 2 pi, take away 7 times √3/4, the area of the triangle, minus 5 times pi over 6 minus √3/4, which is the area of the segments. Now that gives us a final answer of 7/6 pi minus √3/2 centimeters squared, which is about 2.799 if you did it as a decimal. If you got that answer, really well done, because if you haven't seen one of these before, this can be quite a complicated problem to approach. If you did it a different way, let me know down in the comments below. And all that is left to say is thank you so much for watching. If you enjoyed this video, please drop a like on the video. And if you're not already, please consider subscribing to the channel, because I upload a new problem solving video every Monday at 5 p.m. Thank you so much for watching. Have a great week, everybody. And I'll see you next Monday for another problem solving video. Until then, bye-bye.